Hey, how you doing? This is Mel Strong, and this is a lecture on air pressure and wind. Now, we've talked about air pressure in the previous lecture, and what we said is we looked at an animation like this, and we talked about how air molecules fly in a straight line until they collide with something, so they collide with each other, or they collide with surfaces. So every surface that's exposed to the atmosphere is being hit by air molecules millions of times a second, and that produces a pressure. Now, the Earth is trying to pull all of the air down to the ground, and it can't get it all down there, but what it does do is it increases the amount of air that's closer to the surface, which increases the air pressure that's closer to the surface. So as you go up into the atmosphere, there's less air molecules flying around, so there's less air pressure. So we have some units that we use to describe air pressure, and one of them is, maybe this is the one that's familiar to you, it's PSI, pounds per square inch. It's the easiest one to visualize. So imagine 1 inch by 1 inch square. So if I have 15 psi, that means I got 15 pounds pushing down on each square. Okay. Now psi we use in tires. So if you look on the side of your tires, they'll have a psi rating, or inflatable toys or balls or whatever, that kind of thing. They will have psi ratings. Well, the atmosphere could be measured in psi. And so if you go to the sea level, the air pressure is pretty close to 15 pounds per square inch. So think about what that means. That means if you're standing at the ocean, for every square inch on your body, you've got 15 pounds pushing. So the question is, why don't we notice this? Right? So if I take my hand and think about, okay, how many square inches could you draw on your hand? So I don't know, let's just say 6. Okay, I can draw 6 square inches on my hand, right? So if I hold it out, that means I have 15 pounds roughly on every one of those 6 square inches. Well, that's 90 pounds. So how is it possible I can just do this, right? It's like it's no big deal. And I really don't feel anything. So to answer this, think about what it's like to be in deep water. So if you've ever dived deep, let's say you go down to the deep end of a pool. Let's say you had some way that you could like sit on the bottom of the deep end of the pool. What you would notice is that the water pressure is confining you from all directions, but all the water is above your head. So in other words, you don't feel the water from the swimming pool pushing down on your head only. It's all around you. It's a fluid. Well, the atmosphere is also a fluid, and it behaves in a similar way. So when I hold my hand out, yes, I have whatever it was, 90 pounds pushing down, but I also have 90 pounds pushing up. And those two forces cancel each other out, and I don't notice a thing. So this is the thing that kind of takes a little bit getting used to. All the atmosphere is above my hand, right? It's all above all the atmosphere is up there. But the force pushing down from above is the same as the force pushing up from below. And that's the nature of a fluid. Okay, so most of the time, we don't notice air pressure unless there's some weird imbalance of it. Now, PSI, used for tires and toys, but turns out we generally don't use it for weather. Okay, we have a couple other ones that we use instead. Now, to get to some of the new or the other units that we use, so as you know, if you have a fluid and you have a straw and you create a vacuum, right? You suck air out of the straw, that liquid will go up the straw, right? And then you've probably done a thing where you suck on a little bit and put your thumb over it and it'll stay there, right? Because you've made a vacuum in here. There's less air pressure in here, and that will suck up the liquid, right? Okay, well, for many years, engineers are trying to figure out how do we get water up a multi-story building, right? So this was years before electricity, and they were trying to figure out if we had a cistern sitting down here, water tank, couldn't we put like a really tall pipe and suck it up, right? Couldn't we do that? So they tried this, and it turns out that no matter how hard you try, you cannot suck water up more than about 34 feet from where it originated from. And it doesn't matter. You could have 1,000 people all sucking on this straw, and it will not go beyond 34 feet. Of course, they weren't actually using humans to suck. They were trying to make a machine that would act as a vacuum pump that would suck the water up. And they found, well, that's weird. Doesn't matter what we do. We just can't get beyond 34 feet. Now, this problem had been known for a while, but here's a weird thing. When they did this, and not only did it stay at its 34 feet mark, but they also noticed that the exact level kind of changed a little bit with the weather. And so if it was sunny, clear day, it seemed to be a little bit higher. And if it was a cloudy, rainy day, it seemed to be a little bit lower. So they lost. That's kind of weird. Now, this was a problem that had vexed people for a long, long time, because one of the biggest problems that still actually faces miners today, but especially in ancient times, is if you dig a deep underground mine, it can easily get filled with water. Right? Groundwater comes in here, and that's a problem because you're trying to dig out the ore, but it keeps filling up with water. So for a long time, like hundreds of years, people have been trying to figure out, how do you get water up out of a hole? And so they've been trying different vacuum techniques to do this. So 1600s, Torricelli was a scientist, and he was trying to figure this out. Why is this 34-foot limit? Why does this happen? And as he was messing around with this, he figured out that, it's difficult to have a 34-foot pipe with water in it to experiment in the lab. But what you could do is, if you had a denser liquid, you could kind of shrink the whole thing down. And so he found the densest liquid he could find, which is mercury. And he found out that if he took mercury and he filled up a tube that's closed on one end, and he tipped it upside down and he put it into a bowl of mercury and he let his thumb off, that the mercury would fall down a certain amount. Okay? And now at the time, they didn't understand anything about air or air pressure. They didn't think air had any pressure, and they didn't know what a vacuum was. But this little experiment proved that actually you can make a vacuum. There's no way air could have gotten into this little hole. And let me just point out that scientists were balling back there. Look at that outfit. I wish we were still wearing that today. So Torricelli fills this tube with mercury, dish with mercury. So this is what he's got here. There's liquid mercury sitting in this bowl, and he's holding this glass tube here. And what happens is the atmospheric pressure pushes down on the surface of mercury, pushes it up the tube to a certain level. Okay, so this was the first time that anybody realized that the atmosphere actually has pressure. Now, the other thing that he noticed, just like the guys that were trying to suck water up to the top of the building, is that the height of this would change a little bit with the weather. So when it got sunny, this little column of mercury got a little bit higher. And when it was cloudy, it got a little bit less. And the really weird thing is it seemed to be able to predict the weather. So if he saw it starting to climb, then he knew it's going to be sunny weather. And if it started to fall, started to go down, he knew it's going to be stormy weather. Now, this freaked a lot of people out. And Torricelli is contemporary with Galileo. These two guys knew each other. And they were experimenting with this in total secret because they figured out if anybody saw this, they'd be accused of witchcraft. It was freaking them out too. Like, they couldn't figure out how in the world can this thing predict the weather. But it seemed to be able to do it. And so what he had inadvertently invented in this experimentation was something that we now call the barometer. And the barometer works, at least the version he made, is, so here's the Torricelli barometer. You got a pool of mercury, and you got the tube. Atmospheric pushes down, pushes it up the tube, and you have this column. And so the way they would measure the air pressure is that they would measure the height of this column from down here. So if the air pressure increases, the more mercury gets shoved up the tube. If the air pressure decreases, less mercury gets shoved up the tube, and the column falls. And so what did they do? They measured this distance in inches or in millimeters. So a unit of air pressure became inches of mercury or millimeters of mercury, and it was just this height. That was the unit that they figured out. Now, over time, people dropped the words of mercury, so it became millimeters or it became inches. So an air pressure reading might say 30.06 inches. And that, you just have to know that's what they're talking about. They're talking about inches of mercury in this barometer. Well, the problem with this setup, as I've showed you, Torricelli didn't know this, but you never want to touch mercury. Okay, it's extremely poisonous. If it touches your skin, that's bad news. But even like in this instrument that he's got, there's open mercury in this bowl, and mercury actually evaporates, and mercury vapors are extremely poisonous to cause brain cancer, all kinds of trouble. So an actual mercury barometer, this is what one looks like, and they've got it all kind of covered in glass to prevent the mercury vapors to come out, but it's not something you want in your house. And so over time, people figured out other ways to do this, other ways to measure air pressure. And today, we don't use mercury. We don't have columns of mercury. But we still use the unit inches. So here's a more modern barometer, and it says inches right there. And then you can see the numbers 29, 30, 31. So this dial tells you how many inches a mercury barometer would be if you had one, right? But nobody uses them anymore. So this inches is a holdover from an ancient time that we don't use mercury barometers. We haven't used them for over 100 years. You find one in the museum maybe, but that's it. So a more modern unit that we use, besides inches, is something called millibars. And sometimes that's abbreviated MB, or sometimes it's abbreviated as MBAR. And then there's another one that's called hectopascals, HPA. And this gets really confusing. I don't want to get too deep into this. A millibar and a hectopascal are the same thing. They're just different units. In this class, I'm just going to be using the word millibar. So in this barometer right here, it says MBAR. And you see the numbers that go from 950 all the way around to 1070, right? The ones on the outside. So those are millibars. It's very difficult to visualize a millibar, and it's a mathematical thing, and we're not going to get into it. So all I'm going to say is that at sea level, there's about 1,013 millibars, okay? And that's going to have to do for this class because we can't get into exactly what a millibar is. So here's another barometer. This is using HPA, hectopascals, which again, for this class, it's the same thing as a millibar, okay? Just another way of writing it. And again, you see the numbers are in the 900s to the low thousands. So because air pressure varies with height, we could write out what the air pressures would be at some different locations on Earth. So at sea level, say for San Francisco, like we already said, it's about 14.7 psi. Turns out that's pretty close to 30 inches of mercury if you're using the Torricelli barometer. In millibars, that's 1,013. Okay, so as you go up to Albuquerque, our pressure is about 12 psi, which is about 24.5 or so inches of mercury, and about 834 millibars. You get to the top of Sandia Crest, you're below 10 psi, you're 20 inches of mercury, 678 millibars. And if you went all the way to the top of Mount Everest at 30,000 feet or so, it's about 4.5 psi, and you're less than 10 inches of mercury and 300 millibars. So as you go up, no matter how you measure it, the amount of air pressure decreases. Now the thing is, we see these big changes in the air pressure from elevation. And that's true, but that's not actually what we're interested in. What we're interested in is that these values actually change a little bit with the weather. So this is what we're talking about with Torricelli and Galileo, looking at that little column moving up and down like it's telling us something about the atmosphere. So these numbers are average values. So in Albuquerque, our average value is 834 millibars, but it goes up a few millibars, it goes down a few millibars. And that's what we're interested in, is that little change. So why would it change? Well, If you remember way back in the lecture on clouds, we talked about how the atmosphere is divided into two parts that we talked about, the troposphere and the stratosphere. Winds that are way up in the upper part of the troposphere, up by what we call the tropopause, if you remember that, they sometimes come together and converge. And if they do, it turns out that air, when it crashes into each other, for reasons we haven't really got into yet, but we might later, it can't really go up into the stratosphere. Instead, it goes down. So when winds up here converge, and this word aloft, that just means up above our heads, winds aloft, or the winds up there, when they converge, that forces air to go down. Well, when you force air to go down, it compresses, and when you compress air, it warms. Well, what happens when you have a column of compressing, warming air? Well, that air is very difficult to form clouds in. Remember, for clouds, we want air to rise, and this air is sinking. It's going the wrong way, and it's getting warmer, and we need air to get cooler. So cloud formation is very unlikely, and if you remember from the convection lecture, we talked about stable and unstable air. This makes stable air. So all of this is to say that when this whole thing, when these winds aloft converge, all these things happen, and you as a person on the ground notice that the air pressure has increased. So if you get the Coriolis Barometer, when this is happening up here, the column of mercury is rising. And so they talk about the barometer rising. That means that column is going up. Even though we don't use mercury today, we still use that term. The barometer is rising when this process is happening. Now, on a map, what we would do is we would draw a big H on the map to represent the center of high pressure. Now, in my drawing here, this looks really small. That's misleading. This process, this column of air, is going to be the size of several states, big states. I'll show you that in a little bit. Now, maybe the winds aloft will diverge. So this is the opposite. So instead of moving together on a collision course, they tend to diverge apart from each other, and that essentially kind of creates a vacuum. There's a lack of air here. And so what happens is air rises up from the surface to replace the vacuum that's being created. Well, whenever air rises, it expands, and expanding air cools. And what we've said before is that that's what you need to make clouds, right? You want air to rise, it expands, it cools, you hit the dew point, you get a cloud. This is what contributes to unstable air. Okay, so whenever you have this whole process of winds diverging aloft, air is rising, you're making clouds, you're making unstable air, and it's kind of like a giant vacuum cleaner above your head that's sucking air up away from you, you will notice that the air pressure down here decreases. Now, it's not like there's a literal wind flying up from the ground. It's much more subtle than that. But if you got one of those barometers, you'll notice that the air pressure is going down when this process is happening. And so on a weather map, we will put a big L to represent a low or center of low pressure. And again, this process is much larger than this diagram implies. So on a weather map, we will plot H's and L's to kind of look like this. So from this, we know several things now. How would you predict the weather, say, right here in Colorado? Well, there's a low there, so we know the air is rising. We know rising air is conducive to cloud formation, so it's probably cloudy here. We don't have enough information to know if it's raining or not, but we have a pretty good chance that they at least have cloudy skies. Okay, what's the air here doing? The air here is sinking. So what's their weather like? Probably clear skies, sinking air. The air is sinking, warming, and it's making stable air. You can't really make convection, so they probably have clear skies. Now, there is a couple other ways besides the two I just talked about to make highs and lows. If you have somewhere that's really warm and warm air rises, so here we are out in the tropics, and we've got plumes of warm air rising from the ocean going up and making cumulonimbus clouds, then as you bring air up off the surface, you are lowering the pressure at the surface, and this is called a thermal low. So places that are really hot, like Arizona in the summer, will have thermal lows. So this is a different way to make a low pressure. Anytime you have air that's rising from heat or convection, you will get a low at the surface. And then there's also another way to make a high pressure, and you can get this in really, really cold places. So if you have a blob of really cold air that comes in over the continent, and a classic example is Siberia, right? You're up in northern Russia, and this really cold blob of air comes down and settles over the land. Really cold air contracts, and as it contracts and shrinks, more air kind of fills in above it. And what happens from that is the person that's sitting down on the ground in that really cold air will notice the air pressure goes up. You're kind of like piling more and more air on the surface. And because it shrinks when it's cold, it lets you pile more on top, and pretty soon you got a high pressure at the surface. So this is sometimes called a cold high or cold core high. Now, we can look for some of these features. So here I am at the website we've been to before, earth.nullschool.net. And so by default, it's showing you wind. And what I'm going to do is click the word Earth, and I'm going to click on MSLP, and that's for mean sea level pressure. And this is going to show us air pressure along the Earth. Now, here's the scale. The colors, the white colors are the highest air pressure, and then lower air pressure is the yellow, and then the really low pressure gets into blue, and then even lower than that into red. Okay, so let's look around here. Now, as we look around, we can see, like, for example, here's this big purple blob. This is an area of low pressure. So that tells us air here must be rising. Okay, air here must be rising. And if I look at the United States today, I see that whitish color right there. So that's high pressure. So we know that air must be sinking right there. Okay, so every purple blob you see is a place where air is rising. Every white blob you see, like here's a big one out in the ocean where air is sinking. Okay. Now, I'm going to change the overlay to temp for temperature, and this is surface temperature. Okay, so now the colors mean temperature. I'm going to go over here to our friends in Siberia and notice how you get this big blob of really cold air that's sitting over the continent right now. So that purple, that's really cold air that's coming down from the North Pole. All right, I'm going to switch it to MSLP again for sea level pressure. You notice that this whole blob is now white. That tells us it's high pressure. This is an example of a cold core high. So this is a high pressure due to really cold air that's sunk down, again, from the North Pole, and it settles over the Asian continent. Or we go down to the equator. And notice that I've got some dark purple there, but I also kind of have a general purple hue all the way across here. See that right through there? So that is a thermal low. Right through the middle of the equator, it's so warm and it's so humid, you have constant cumulonimbus in this area every day. And that means air is rising, and that creates a low pressure at the surface. So this is a thermal low, kind of right through there. We see it again over here, kind of goes through Central Africa. It's pretty close to the equator. Right there is the equator, right? So it's kind of around there. And then over here, it kind of does something different. So that is a thermal low. This was a cold core high. And then with each one of these little blobs, there's something happening in the atmosphere where we got air converging or diverging aloft, which is either making air rise or sink in the atmosphere. So with air pressure, we're interested in the changes due to weather, but the problem is the changes due to elevation are far, far greater. So imagine we've got three cities here, San Francisco, Albuquerque, and Leadville, Colorado, and San Francisco being at sea level is going to average 1,013 millibars, plus or minus a few millibars with the weather. But we are going to be like 834 millibars, plus or minus a few. And Leadville, Colorado, being over 10,000 feet up, is going to be at 692, plus or minus a few. So here's the problem. No matter what happens to San Francisco's weather, they will never, ever get air pressure as low as ours. And no matter what happens to our weather, we'll never get an air pressure as high as theirs. So it's really hard to compare numbers because we're all at different elevations. So how do we resolve this? Well, one solution would be, well, what if we had everybody on the continent drill down to sea level, right? They just drill a deep hole and they put the barometer at the bottom of the hole, right? Then everybody's got a barometer at sea level, okay? Then we could compare numbers. That would work, but it would be kind of hard to pull off. So what we do instead is we can actually mathematically correct for elevation. Now, we're not going to do that in this class. We're not going to do the math. Someone else is going to do that for us. But the convention, when we talk about air pressure, and this is kind of a worldwide convention, is we report the air pressure as if we were at sea level. So what happens is they take a pressure reading, say at Albuquerque's airport, and they calculate, okay, what would it be at sea level if we were at sea level? And they mathematically subtract out the effect for elevation, and that's the number that gets reported. So when you check the weather, so here I'm at weather.gov. This is where your tax dollars go to for the best possible weather prediction. They're way better than any kind of other weather service out there. And you look at, so if you go there, you can go click to wherever you live. And here I'm at Albuquerque's airport. And so here's a reading. So things on here we know now, right? Humidity is 29%. Okay, what humidity is that? Well, because it's a number between 0 and 100%, I know that has to be relative humidity, right? There's our dew point. So we've talked about that. Notice this. So here's barometer. 30.08 inches, and then in the parentheses, 1,015.5 millibars. Okay, so 30.08 inches means that if we were at sea level, which we're not, and if we had an old Mercury barometer, which we don't, and we set it up, this is what we would measure that, 30.08 inches of mercury. And then in a more modern unit, 1,015.5 millibars. But these are valid if we drill down to sea level here at Albuquerque. That's what the air pressure would be. So that's how it's reported. So we call this sea level pressure, right? And everybody reports their barometers as sea level pressure. So after thousands of air pressure measurements are taken from thousands of weather stations all across North America, and we mathematically correct each of those for elevation, then we plot the results on the map that kind of looks like this. And this is called a sea level pressure map. And a sea level pressure map, so before we continue, if you're one of my current students, I have this posted on Learn. There's 3 pages. You might want to print these out before we start. If you're coming here from somewhere else on the internet, I have these on my website if you want to download those. So there's 3 pages numbered 1, 2, 3. We're going to start with page number 1. And on the bottom it says sea level pressure map for 1/116. Okay, so first thing is that there are these numbers, 1020, 1025, 1030, 1035. Those are sea level pressure contours. So these are contour lines. And the way you would read this is that if you were to walk right along this line on this day and you're at sea level, which you're not, but if you were, that the air pressure would be 1030 millibars. All these are in millibars. They don't say that. Now, each one of these contours is the same way. If you walk along these contours, you will be exactly at that pressure indicated by the number, and as long as you stay along that line, and if you're at sea level, that's what the air pressure would be. So if I were to walk, say, this way, okay, start in southern Texas and I walk north, what I would notice is that the air pressure is increasing. 1025, 1030, 1035, 1040, right? Or if I start up here in the north, 10, 15, 20, 25, 30, 35, 40, they're increasing towards the center of this big blob here. And in fact, right in the middle, this is the highest pressure of the whole region, this 1040 contour. So no matter which way I go, air pressure is increasing towards this region. So I'm going to put a big H right here for a center of high pressure, okay? Now, What that means is that this whole blob is a blob of sinking air. Okay, so to relate it to something we talked about a few minutes ago, I had a diagram of a person standing on the ground and air is sinking above their head, and I said at the time that it's much bigger than this diagram would have you believe. This is what I mean. This thing is huge, right? It covers all of the western United States and parts of Canada. This is a big blob of sinking air. So there's air coming down from the upper part of the atmosphere, squishing out here. So we could say a few things about their weather right now. High pressure, they're probably clear skies, right? It's stable air, we know that. Another thing that we can tell from this, on this map, notice how, if I look at this part, if I were to walk this direction, the numbers increase. So 10, 15, 20, 25, 30, 35. And then if I walk this direction, the numbers decrease. Okay, so it's analogous to a mountain on the topographic map. So a topographic map would have contours, except they mean elevation. I'd be walking up the hill and then be walking down the hill. Okay, so on a topographic map, this feature right here would be a ridge. This is not a topographic map, it's air pressure, but we still call it a ridge. It's called a ridge of high pressure. And I just bring this up because this term ridge of high pressure, is used in meteorology. And in weather reports, you might hear it used, something like this. They might say, there's a ridge of high pressure building over the Four Corners area over the next several days. What does that mean? That means that there's a high pressure system centered over the Four Corners area, and it's getting stronger and stronger for the next several days. So when you hear ridge, just think high pressure. So even on a map that, like this one, even if you don't really see this particular feature, it doesn't matter. A ridge is just a blob of high pressure. It's a big blob of sinking air. Okay, let's go to the second page. So here's the second page, and it says sea level pressure map 22516. All right, so let's start in the west, and we see 10, 17, 20, 22, 25, 27, 30. Numbers are getting larger towards this blob here. Or if I go from the south, 25, 27, 30, they're getting larger towards this blob. So locally, this is a higher pressure than anything else. So I'm going to put an H here. Okay. Now, let's look over here. And we've got this weird bullseye pattern. And I've got numbers 10, 17, 12, 10, 7, 5, 2, 0, 9, 9, 7, 5. They're getting lower towards the center of this bullseye pattern. Or if I go from this direction, they're getting lower towards the center. So if I walk towards the center of this bullseye, pressure is going down. So this is the center of low pressure. And I put my L right in the center of that thing, right there. So we have, in the country, on this particular day, we have a blob of air that's sinking down, squishing out on the ground on this part, making high pressure. And then we have a blob of air that's rising up. And so we can say a few things about the weather, right? We can say that, well, over here, they probably have clear skies, stable air. Over here, they've got definitely cloudy. And in fact, this is a pretty severe storm system here. And I say that because there's so many of these pressure contour lines pretty close together. This is a pretty strong storm. So all we can gather from what we've talked about so far is that this is rising air, this is sinking air, here's probably cloudy, here's probably clear. Beyond that, we don't have enough information yet to say more, whether it's raining or anything like that. Okay, let's move on to number 3. Okay, so the first thing I'm going to do is identify highs and lows. And so if I look over here to the east, I see 1012, 1010, 1007, 1005, 1002. Numbers are getting smaller towards that bullseye. So that is going to be a low here. Now, our highs are not as clearly defined. There's one over here, and the numbers are kind of cut off, so it's a little hard to see. But 1017, 1020, I think it's cut off. 1022.5, but that's a high over there. I'm just going to put that on there, out over there, over the ocean. There's a kind of a small high over Mexico, so this is 1017 and a half, 1020. That one doesn't have a number, but there's our high right here. There's another little high sitting kind of over the Four Corners area. So this 1020 is bigger than anything around it. So there's a high. Okay, now the reason I have this map is because I want you to pay attention to what's happening kind of in the middle here of the country. These numbers, 17, 15, 12 and a half, 10, 7, 5, 2. So these numbers are decreasing towards the north. Okay, the pressures are decreasing towards this blob up here. This up here is a low, and the map has been cut off so that we don't actually see, these contour lines don't wrap around. They're somewhere up here in Canada, but we don't see them because this is where the map ends. But notice that in our country, how you've got these U shapes, right? These U shapes come down. And kind of like we were talking about a ridge, this thing, if this was a topographic map, would be a trough. If this was elevation, and I was walking across here, I'd be going down, 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 and then up, 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 back out of it. So this would be like a valley or a ditch. So this thing on a weather map is called a trough. And a trough is connected, it's these U shapes that are connected to a low. So the center of the low may not even be where I drew it. Maybe somewhere to the north here. It's off the map. But that's pretty common. So a lot of times where we live, for example, our weather map may be cut off like this. And that's all we see. And we don't know what's above here. But we see that we have these U shapes, and we see that the numbers are getting smaller towards the middle. That's called a trough of low pressure. So kind of like ridge means high pressure, in weather speak, trough means low pressure. So when you hear a weather report and they talk about a trough of low pressure moving across the country, what they are saying is that there's a low pressure center that's moving across the country. The center of the low may not be in our country itself. It may be to the north, but it still has the same effect as the low. So this trough, as it moves across the United States, air is rising in the trough. So you've got cloud formation in the trough. So in your mind, when you hear trough or trough of low pressure, just think it's a low. Okay, it's a low pressure center moving across the country. Okay, so now we're going to return to earth.nullschool.net, and I'm looking again at mean sea level pressure. I did that by clicking Earth and MSLP. So the purple is low pressure, the white is high pressure, and I'm going to zoom in here on this spot out in the ocean. That's a high, and I want you to notice what the winds are doing. So the winds are spinning around in a circle, right? And they're going clockwise. Now right next to it is this low pressure, this blob, and notice that the winds are spinning counterclockwise. Here's another little purple blob, another low pressure, winds are spinning counterclockwise. And that's the pattern that you'll notice here. Let's find another one. Here's another high out in the ocean, clockwise. Here's another big low pressure. This one's a little harder to see, but overall it's going counterclockwise. All right. Now, this pattern is consistent throughout the northern hemisphere. If I have a high, I have air circulating clockwise. If I have a low, I have air circulating counterclockwise. Okay, now let's go down here. Let's see what's happening in the southern hemisphere. So in the southern hemisphere, I've got a bunch of low pressure centers down here by Antarctica. But notice this low spinning clockwise. Here's a low, clockwise. Here's a low, clockwise. That's the opposite of what we just saw. Or over here, here's a high, that white spot, counterclockwise. So there is a rule regarding the winds around highs and lows, but it depends on what hemisphere you're in. So if you're in the southern hemisphere, wind goes counterclockwise around a high and clockwise around a low. If you're in the northern hemisphere, it goes clockwise around a high, counterclockwise around a low. Okay? So why is this? Well, this has to do with the famous Coriolis effect. So to explain the Coriolis effect, let's consider what would happen if the Earth did not spin. If the Earth did not spin, then air would want to move directly from a high to a low in a straight line. Okay? So any winds that we would have would be directly between highs and lows. But that's not what we observe on Earth. What we observe is that winds in the northern hemisphere are deflected to the right. So the wind's trying to move from high to low, but it can't ever get there because it's always being moved to the right, and it ends up going in a big circle around the high in a clockwise fashion in the northern hemisphere or counterclockwise in the southern hemisphere. So to try to explain this, I have one little demo here, and what we're looking at, so imagine this is the Earth and we're looking straight down the North Pole, right? So if I have wind that's moving from the North Pole to the equator and the Earth did not spin, wind is trying to move in a straight line like this, right? Okay, but now let's imagine that the Earth is spinning and the Earth spins counterclockwise on as you look from the perspective of the North Pole, right? So now if I move my wind in a straight line, kind of clumsy, but what I see is that my wind, from the wind's perspective, is moving, it's making a big right-hand turn, right? It turned to the right. And that was simply due to the fact that the Earth is spinning. So I was trying to hold a straight line as I was turning that. So that's one demonstration of the Coriolis effect. I've got a couple videos here that I will also show you.
The Coriolis force is an apparent force that causes moving objects to appear to bend away from their intended paths. This force can be due to a rotating Earth, or in this example, a rotating platform. On a non-rotating platform, we can see that a thrown ball moves in a straight path to the receiver. Suppose the platform begins to rotate counterclockwise, just as the Earth rotates counterclockwise when viewed from above the North Pole. On the screen to the left, we see that the thrown ball moves in a straight line path. However, when we view the thrown ball on the rotating platform, the screen on the right, the camera reveals that because the platform is rotating, the ball in flight appears to curve to its right, and the receiver has to lean to the side in order to attempt to catch it. Even though the ball actually moves in a straight line, people sitting on the rotating platform see the ball appear to bend to the right of its intended path. The apparent bending of the thrown ball is due to the fact that the platform is rotating. The apparent force that causes the bending is the Coriolis force.
So this animation explains Coriolis effect in a little bit different way, and I think it's great, except the graphics aren't necessarily the highest resolution. But we start out, we've got 2 points that are on the same longitude but different latitudes. And so the point is that as the Earth rotates, these 2 points are going to rotate together, right? But if you look at the paths of each of these 2 parcels, they're going to be different. The parcel that was closer to the equator, with a lower latitude, had to travel farther in the same amount of time. So it had to be moving faster. So now imagine that you've got a rocket at the equator and you're going to shoot it straight at this red dot, okay? But because the rocket is at a lower latitude, it has a higher easterly velocity. So it's moving to the east faster than this red dot is for the reasons we just saw. So if you shoot the rocket in a straight line, it appears that it turned to the right. But from the rocket's perspective, it was going in a straight line the whole time. it just had more easterly momentum than the red dot does, and it appears to curve off to the right. Then you can think of the opposite case. Now imagine the rocket is at the North Pole, and you're going to shoot it straight at this red dot. Okay, but now the red dot at a lower latitude has a higher velocity to the east, and the rocket doesn't have any. So again, it misses, and from the perspective of the rocket, it's going in a straight line, but the perspective of someone on the ground looking at this, it looks like it went too far to the right. So no matter which way you go in the northern hemisphere, if you move it in a straight line, you're actually being deflected to the right from the perspective of the person on the ground. That's what the Coriolis effect is. And the Coriolis effect only works on something that's a very, very long distance. So there's a lot of folklore and urban legend about Coriolis effect. So a common one is that toilets flush clockwise in the northern hemisphere and counterclockwise in the southern hemisphere, or maybe it's opposite. The Coriolis effect only affects things over a very, very, very long distance. So you can make a toilet flush either way in either hemisphere. It doesn't change it. If that was true, if the Coriolis effect was so strong that it would rotate water that only moved a few inches, it would basically be impossible for us to drive cars. We would just go flying off the road to the right, or even if you just started to run, everybody would be flying off to the right all the time. So it doesn't happen that way. It just works on things that are operating on very long distances. So let's return now to our those three handouts that we were looking at earlier. So these sea level pressure maps. And so now what we can do is we can make predictions about the direction of the wind. So the first one we looked at, this is map number 1, high pressure, this big blob here. I know now that winds travel clockwise around a high. So I know that around this high, I'm going to have winds that are moving in a clockwise fashion. Now, in this class, what we're going to do is we're going to assume that the winds are traveling parallel to the contour lines. So in other words, I know the wind's going to be doing this. So I'm drawing lines that are parallel between these contours, but they're overall going in a clockwise fashion, right? So if I asked you, okay, what is the wind? Well, let's say in Albuquerque, what's the wind in Albuquerque doing? Well, right here, if you drew an arrow, the wind is coming from the southeast and is traveling to the northwest. So here's a convention with wind. Wind is always described in the direction it's coming from. So if I have a north wind, that means it's coming from the north, right? If I have a westerly wind, it's coming from the west, okay? So we can predict which way the wind's going to be blowing by simply thinking about, okay, do I have clockwise or counterclockwise? And then drawing little short segments that are going clockwise, in this case, around this high, but staying parallel to these contour lines. So let's do another example. Let's do page 2. So we've got wind that's going clockwise around the high, and let's look at the low instead. So we know wind goes counterclockwise around the low, and again we're going to say it goes parallel to the contour lines. So wind would be going kind of like this. So I'm drawing little segments, right? Little segments of arrows that are going overall counterclockwise but staying between the contour lines. Now, realistically what happens is that air that's aloft, up above our heads, is moving exactly parallel to the contour lines just like I described. What happens here on the ground is a little different. Wind hits trees and buildings and mountains and it slows down. And what happens actually is it spirals inward, kind of like this, when it gets close to the surface. If that's showing up or not, it's spiraling inwards. And And near the surface, high pressure spirals outwards near the surface, like that. But for this class, for the exercises we're going to do, we're just going to draw the wind arrows parallel to the contour lines every time. Okay, and that way we'll just be consistent on the wind direction. All right, so here's an example of what I could do. I can say, all right, what is the wind direction in Tennessee? Okay, so there's Tennessee, and we know we have counterclockwise, so it's coming around this way. So what would the wind be like right there? Okay, so right there, I'm going to draw a straight segment that is parallel to those contour lines, and it's coming from the northwest, right? That is a northwest wind. Okay, so if you're one of my students, you'll have an exercise where you're going to be asked to identify the wind direction on a map like this. So the correct answers you want to give are something like north or northwest. Sometimes I get answers clockwise or counterclockwise. So we never go outside and say, oh man, it's blowing counterclockwise out here. From our perspective on the ground, the wind's coming from one direction only. And what I'm asking you is to figure out what that one direction is. So you're drawing your wind direction as straight segments. Okay, so let's do another one. What is the wind like in Minnesota? All right, so here's Minnesota. And so here I'm between a high and I'm between a low. So how do I know which one to pick? So we'll do an example with each. So let's say I do the one with the high. I know I got clockwise around a high. So I know I've got wind coming around here, this going this way. So I want to draw a straight segment in Minnesota. So right there would be the wind direction, right? So that's consistent with clockwise around a high. It's coming from the north to northeast, right? Okay, so let's say instead I picked the low. Low, counterclockwise around the low. So I've got wind coming around this way. And when I get down here to Minnesota, I'm going to draw a straight segment that's approximately almost going the exact same direction as the first one we did, also from the north or a little bit northeast. So it doesn't matter which one you pick, you should get the same answer. Let's move on to number 3. So how would we deal with this trough? So in a low, let's look at this low out in the ocean first. You got counterclockwise around the low. So I can draw little straight segments around the low, like this, right? And it's no different around the low up here. The low up here, you get straight segments coming down and going around that low and counterclockwise. And you just extend that all the way down. So down here in this trough, I would have wind doing this. Right? So I could do the same thing. I could ask you what's the wind direction at any location here within the trough. Now, I'm going to pull up number 2 again. I want to point out something that we alluded to a little bit but didn't talk about. Notice the spacing between these contours is very tight, and the spacing between these contours is very open, right? So if I were to walk, let's say I were to walk straight across this direction here. If I were to walk straight across this direction, I would notice that the pressure as I move this way is decreasing, but not by much. Whereas if I walk this direction, I would notice that the air pressure is decreasing, but it's decreasing at a much more rapid rate. Okay, so we have a name for this. It's called pressure gradient. Here, as I walk along these tightly spaced contours, the pressure is changing rapidly as I walk, right? Here, not so much. We would say this has a high pressure gradient, this has a low pressure gradient. What would the pressure gradient be like if I walked out through here? Well, we're not crossing any contours at all, so the pressure gradient itself is essentially 0. So there's very little to no pressure change in here. So very low pressure gradient. Or if I walk through here, or swim, I guess it would be, across the ocean this way, the pressure is just barely changing right through here. So it's a very low pressure gradient. This is a higher pressure gradient. Okay, so turns out the wind speed depends on the pressure gradient. So winds blow faster where the pressure gradient is stronger. So if I had to shade in, say, where is the highest wind speed in this diagram, the highest wind speed are going to be the locations where the pressure contours are closest together. So you have very, very high wind speed, for example, all around this low here where these pressure contours are very tight. What about out in here? Out in here, the winds are probably non-existent out here, or the winds are very, very slow out in here. So you can use the spacing of the contours to predict how fast the wind is going to blow. Okay, so to conclude what we've learned here, just using air pressure from a barometer, we can create a sea level pressure map. From that map, we can identify places where the air is rising and sinking. From that, we can figure out where it's going to be cloudy and clear. Then we can use the contours to figure out the direction of the wind, and we can use the spacing of the contours to get a relative sense of wind speed. So all of this is just due to one thing, which is air pressure. All right, thanks for listening.